In today's lesson, we are going to be looking at vector addition. So in our previous lessons, we've looked at the components of vectors, breaking vectors up into horizontal and vertical components. Now we're going to look at if we want to add vectors together. So there are going to be kind of multiple ways that we can do it, and we have to look at some just key terms first before we get into it. So when we want to add two vectors, the sum of two vectors, or the sum, or what the result is called the resultant. We might use it as an R, right, if we're talking about just the vector, or if we're talking about the magnitude, we'd say something like that. But when we're comparing the two, the sum of two vectors is considered the resultant. And when we're going through and adding vectors, it does help to know a little bit of terminology about the vectors themselves. The first one, this vector AB, we've mentioned this before, so this is vector AB. The two parts of the vector, right, you have your tail, which tends to be the first number as well, or the first letter. So right over here, AB. So this part is the tail, or where we start, and then we have the tip of the vector, or the head, maybe it might be called, basically the arrow part. So you have your tail and your tip of each vector, and that's going to be important for when we look at the different methods for adding vectors. So there are going to be three methods that we look at. We're going to first look at if we're given the vectors geometrically, we can actually see them. We can see our vectors here. The first one is going to be called the parallelogram method. And the methods are basically based off of the shapes that you're creating. So in the parallelogram method, the first thing you're going to do is you're going to draw them tail to tail. So what that means is you're basically going to connect the two tails together. So if I was to draw them, I'm going to have, it doesn't really matter which way, I'm just going to put them, right, so I have, there's one vector, this is V, and then U. I'm going to make sure that when they connect, their tails are connecting. So this would be going down, one, two, 3. So I'm going to draw them tail to tail. The next step is I'm going to create a parallelogram. Or I'm going to assume that they're a parallelogram, right? That these are the two sides of a parallelogram. So what I need to do then is just basically copy those two sides, right? Parallelograms mean opposite sides are parallel, so I'm going to copy those two. So from this point, right, maybe if it helps if I do color code it. So now I've created a parallelogram based off of those two vectors, right? And it's kind of basically I just take that pairing of the tail to tail part here, and I flip it over here to make a parallelogram. Now the resultant, I don't have the resultant yet, but the resultant, or the sum of my two vectors, right, is basically going to be the diagonal. So from one end to the other, that's our resultant. So the resultant is the diagonal. So if I add vector u plus vector v, this resultant is the sum of them. So the r is equal to u plus v. Now the triangle method is something similar. This one is probably going to be more of the one that we use, but it doesn't hurt to know the different kinds. So in our triangle method, our first step, what we're going to do is we are going to do not tail to tail, but we're going to draw tip to tail. So basically we're going to connect them from one, right, we're going to basically join them together in the same kind of like a continuation almost. So I'm going to start with you. Doesn't really matter which one you start with. I'm going to start with U. And then I'm going to put V right at the tail. So there I have V now. And the next step for 2 is to create a triangle. So I'm going to create a triangle that joins where I ended, or where I started, and where I ended. And that's going to be the resultant. Right? So I create a triangle from that, and I draw the resultant. And again, in this case, the resultant is equal to vector u plus vector v. Right? We're going to focus more on the triangle method than the parallelogram method, just because if we have to answer specific questions or determine magnitudes, we do already have a lot of formulas involving triangles that makes it easy to find magnitudes or side lengths, you might say, of the triangle. The other method is the component method. So we looked in a previous lesson if we had components, and when we're dealing with the component method, it's really very straightforward. Basically, you put this over here, down here, step 1, you add the horizontal components. And the second part, you add the vertical components. And that will give you the new, or the resultant. Right? So if we wanted, in this case, we wanted to do u plus vector v, right? That is going to result in the horizontal components added up. So the horizontal, again, are the first one, so -1 plus -3. And we have the vertical components added, 3 plus 1. Vector u plus vector v is equal to, we have -4, 4. And if I were to go back and look at my resultant just to see if it does work, I can see I can go over 1, 2, 3. Did I do the math wrong? Maybe I added up, or maybe it's a different vectors. Oh yes, it is different vectors. Because yeah. So these are different vectors than the two, but this is what it would work out to. If I were to do it with this one, we would have 1, 2, 3 over, and over 1, no, over 1, and then down 1 over 1, 2, right? So this would be slightly different than the one we just had, but the idea would be the same, and it would work out to give us the same values. All right, so component method, we add the horizontal and vertical components to get our resultant. Right, so this is the resultant. And then with our triangle and parallelogram, when we're geometrically given when we're geometrically given the vectors, we can draw either a parallelogram or triangle with them to get our resultant. So let's look at a couple examples working through them. So the first one, determine the magnitude of vector AB, then determine the quadrant bearing of the resultant. So basically, I need to add these two together, and I need to figure out what is the quadrant bearing. So I need to figure out the angle for them. So in this case, I'm going to combine them. I'm going to do the triangle method. So I'm going to draw them together. So we have A here. So we have 2, then from tip to tail, B for the resultant is going to be the diagonal to make the triangle. Because these are, this is a horizontal and vertical line, it forms a 90-degree angle. Now for the resultant, when I want to figure out the magnitude, or the magnitude of AB, or we can say the magnitude of the resultant, different ways you can represent or label that, that diagonal. it is going to equal to the magnitude of a squared plus the magnitude of b squared, right? We can use Pythagorean theorem to figure out this diagonal. And again, you could use different symbols, but we're just kind of using the specific notation for magnitudes. So it should be resultant squared. So resultant squared plus the magnitude of a squared plus the magnitude of b squared. Right? And we're going to go through and solve. So we have 2 squared plus 4 squared. Magnitude of r squared is equal to, this works out to 4 plus 16 or 20. If I want to find just r, I have to take the square root of 20, or I could say 4.5 newtons, roughly. If you want to keep it as the exact value and leave it as the radical or the root of 20, you can do that as well. So we have the magnitude now. Now we need to figure out what is the quadrant bearing, right? What is the degree or the angle? So we need to figure out this portion here. So now we're going to use our trig that we've learned before to figure out what is that angle. So I have my angle. Based off of that angle, I have my opposite and my adjacent. So the trig ratio that deals with opposite and adjacent would be tan. So tan theta is equal to O over A, or 4 over 2. I'm going to bring the tan over, so tan negative 1 of 4 over 2, or 2, is equal to theta, and I get that theta equals 63 degrees. So this angle is 63 degrees. So we could say, if we wanted to, therefore the resultant is equal to 4.5 newtons, and then we could say east 63 degrees north, or we could say 4.5 newtons north 27 degrees east. Usually we like to use north and south as our first values, and then so many degrees east or west, and we get the 27 from, again, if we assume a vertical from north, this would have to be 27 degrees. So just using the different components, similar to some of the previous lessons, horizontal and vertical components, we've used trig before in previous units to basically figure out our degrees. Right? So we're kind of combining a lot of the different concepts that we've looked at in previous units into this one. The next example, we want to determine what is A plus B. Right? So we want to basically determine the resultant of these two vectors added together. Again, what I'm going to do is I'm going to create a triangle out of them. And there's two kind of ways you could do this. One is creating a triangle. So I'm going to go through, create the triangle. So I have 12 tip to tail, then 21. And because it's east 26 degrees north, that means east, 26 degrees north. So what I can do is I can use that to help me figure out what this angle is. And the reason I say that is because the resultant is going to be this side. So it does help if I know what the inside angle of this triangle is. So the inside angle of this triangle, though, is 180 minus 26, which is 154. So this is 154 degrees. So I have enough information now to figure out the magnitude of that missing side. And there's going to be, the way we're going to look at that is if I look at that triangle, maybe I'll just try to redraw just the triangle just to make it a little bit clearer of what we're actually looking at. So 12, 21, 154, and we're looking for this side. This is a non-right angle triangle. So what we can be doing is we can use cosine law. So for this method, we are going to be using cosine law to determine the missing side. So cosine law, if we're missing, our x squared is equal to, we said it was a squared plus b squared minus 2ab times cosine of, in this case, x. X squared is equal to 12 squared plus 21 squared minus 2 times 12 times 21 times cosine of 154. When we go through and we calculate all this, we should get that x squared is equal to 1038, square root both sides, and we get that x is equal to 32.2, and it would be meters per second. So in this case, we can say that our resultant, the magnitude of the resultant, is 32.2 meters per second. So we have one portion done. The next portion that we need to do is now we need to figure out what is the angle or what is the bearing, right? So what we want to do is we want to figure out then what is this angle here. If I know what that angle is, then I can use the idea of being 108, or of north being 90 degrees from there, and I can figure out what that missing angle is, or I can figure out what the bearing is, or I can figure out what the coordinate degree is, or the coordinate bearing. So to figure out that angle, I'm going to need to use sine law. So sine of that angle over 21 is equal to 32.2 over 154. Cross multiply, we get sine. I messed it up, sorry. Let me go back. Not 322, it's sine 154 over 32.2. Cross multiply. So we get 32.2 sine theta is equal to 21 sine 154. We're going to bring the 32.2 down, so we get sine theta is equal to 21 sine 154 divided by 32.2. Then we can get sine by, or theta by itself. So we get sine -1 of all of this, 21 sine 154 divided by 32.2. And we get theta is equal to 16.6 degrees. So now we know this angle here. We know this angle now is 16.6 degrees. So we could use that to figure out the magnitude. So we could say that the magnitude, or that the vector r, therefore r is equal to 32.2 meters per second. We could say east 16.6 degrees north, but we do want it to be, we do technically preferably want it to be north so many degrees east. So we can figure out the difference. This would have to be 73.4 degrees. So we could say north 73.4 degrees east. Or if we want the quadrant or the true bearing, right, depending on how we want it labeled, let me just kind of reorganize some of this here. We could say or 32.2 meters per second, and we could just say 73.4 degrees, right? Because true bearing is basically a 3-digit degree, so 073.4 degrees from north. So that is one way to solve that question, and that is using basically trig, right? That's looking at creating the triangle and so on. The other way, I'm going to divide the page up here. So the other way that we could do it, let me just draw a straight line down. Doesn't need to be dotted. So the other way that we could do it is looking at the components. Right? So this way we'll say this one way, this was triangle. This way is going to be component. So what we're going to do is we're going to look at each vector and we're going to look at the horizontal and vertical components. So for the A vector, that can be broken down into a horizontal component that is basically 12 and a vertical component that is 0. For the B vector, we don't know what the two components are, but if I were to draw it as a triangle, I know this is 21. It's east 26 degrees north, so this is 26 degrees. I can use my trig, similar to my last lesson, to figure out the horizontal and vertical. So the horizontal, right, is going to be my adjacent, opposite. So for my horizontal, it'll be cosine 26 is equal to the horizontal over 21. Get the horizontal is bring the 21 up, 21 cosine 26 gives me 18.9. So my horizontal component is 18.9. Then the vertical component is going to be, I'll do it over here, vertical component. So the vertical component would be, just rearranging stuff to make it a little bit neater. The vertical component would be sine. So sine 26 is equal to the vertical component, or the opposite, over 21. Bring the 21 up. 21 times sine 26 is equal to 9.2. So that is my vertical component. Now we said if we know what the components are, right, in the component method, we can just add them up. So the resultant then is going to equal 12 plus 18.9 and 0 plus 9.2. So just adding the horizontal components and adding the vertical components. So I get that my resultant is 30.9, 9.2. Now I don't have the degree yet, but I can determine that by creating another triangle. I know the horizontal is 30.9, the vertical is 9.2, right, for my resultant, and I can figure out what the angle is. So this is, again, my resultant. And I can figure out what this angle is of that resultant. So again, I have my opposite and adjacent, so tan theta is equal to opposite over adjacent, 9.2 over 30.9. Theta is equal to tan negative 1, 9.2 over 30.9. And I should get 16.6 degrees. So it gives me the same answer in the end. So different ways you can think of going through and kind of adding these together. You could look at it as more of the triangle method. You could break it down into components and look at it that way. Whichever way you feel is easier. Now this one was a little bit easier to do the component method because we are given a vector that was easily distinguishable what the horizontal and vertical are. If you had two diagonals, then maybe it would be a little bit harder. The last example, so in a parallelogram EFGH, J is the intersection of diagonals EG and FH, and we want to name the vector that's equivalent to each expression. So we want to add these different vectors and write the vector equivalent. So EF plus FG, right? So EF is this vector here. EF, oops, sorry, doesn't really matter. We're looking for, so E would be the tail, F would be the tip. So we go in here. Right. So the resultant, use red continuously, would be this. So that would be the resultant. So the resultant in this case would be the vector EG. Now, one thing to note, if you're doing something like this where you have kind of a shape that's predetermined, or just in general, right, you want to remember you can only add tip to tail. Right, so when you're adding vectors, you can only add tip to tail. So what you should really be looking for when we're adding vectors, something like here, the first one, the two middle letters should be the same thing. Right? That's how you know that you've added tip to tail. Right? So EF, right? I'm just going to go back and do it again. EF, if I'm going in this direction, E to F, there's my tip, F to G, my tip's over here, so my tail's here. So this is a tip to tail right here. So again, that's just kind of one thing you can kind of look for when you're kind of adding vectors in this kind of situation. You're looking for, do the two middle letters match? So FJ is the next one. So F to J, we use this gold one just to make it a little bit clearer. So F to J, and then J to H. What would be the resultant there? So here, this one might be a little bit different because like, how do I represent this? But again, you go from the start to the end. This would just be the same thing as saying FG. Right, start to the end. Or sorry, not FG, sorry. FH. For the next one, EF, so going E to F, F to H, and then H to G. So the resultant, right? The resultant is just basically the difference from like the beginning to the end, right? So even though we went a very long distance, we went down and we back up and went down, the resultant is still going from here to here. So the resultant in this case is just EG. Even though it might be like, well, how does that make sense, right? It shouldn't it be a little bit longer? You're basically looking at where, or like the displacement, so to speak, where you started and where you ended up. So in this case, all these vectors work out to EG. Next one, EJ. So EJ going here, and then FJ or HJ. So HJ is going here. Right? So geometrically looking at it, I can't really add those two together. Right? It doesn't really kind of make sense. How does that work? Right? But what we can do is we can look in our shape and find equivalent or equal vectors. Right? So if I look at this one, HJ, this vector would be the same as JF. Right? So this is the same as vector JF. So what I could do is I could basically rewrite this as EJ plus JF. EJ plus JF. And then the resultant of that would be EF. I could also look at the similar thing. So if it is EF, it could also be the same thing as like HJ would also be an equivalent vector, right? We talked about that in the first unit. Equal vectors are basically same direction and magnitude. It doesn't matter the location or position. So you could say HG as well would be an equivalent vector or the result would be the resultant as well. And then the last one, FG, so FG plus GF, so then going back, do that in two different colors just because it might be hard to see with the one. So E or FG and then GF. We start here and we end here. So what is the resultant? What's the result of that movement, you might say? Well, we haven't gone anywhere, right? So we haven't gone anywhere. So what we say, we call it a zero vector, right? So this is a zero vector. So it's a zero vector, right? Basically zero with the arrow or the harpoon above it, right? So a zero vector also has a magnitude of 0 because it hasn't gone anywhere. There's no length, there's no magnitude to it, and there's no direction. So you can have zero vectors. Basically, there's dots, or the resultant is just a dot, right? Because there's no magnitude, there's no length to our vector. If we were drawing it, there's no horizontal or vertical component, or they're both 0. There's no horizontal and vertical component, and there's no direction as well. So you can have zero vectors. So main thing from this is just looking at how we can add vectors in different ways, right? Geometrically, just with the shapes, using the triangle method or the component method to add them together, as well as which will allow us to determine the magnitude and the coordinates, or the bearing. So we see one more the triangle in the component method, or we see kind of a more standard one. So a lot of this is going to rely on recalling, right, trigonometry, right, sine law, cosine law, trig ratios, Pythagorean theorem, to answer some of these questions. So if you are unfamiliar with that or you don't quite remember, please make sure you go back and take a look at those lessons.